So, in the last class we had started our discussion on diffusion and dispersion. In the beginning I had said that there are two mechanisms, convection and diffusion. Convection is along the fluid velocity streamlines and diffusion is due to the fluctuating velocity of the molecules. Convection takes place only along the flow. So, it cannot take place perpendicular to the flow in the cross stream direction or across surfaces, because typically the flow velocity perpendicular to a surface will be 0 for a stationary surface, or when you are moving with the same velocity as the surface velocity. So, that transport has to necessarily take place due to diffusion. Diffusion is due to the molecular fluctuating velocity. Okay. Even though there may be no net flow velocity, all molecules are in a state of constant fluctuating motion due to the thermal fluctuations at any non-zero temperature. The root mean square velocity in each of the translational modes is half kT, and in 3 dimensional space there are 3 translational modes. Therefore, the root mean square velocity is given by the relation half mv square is equal to 3 by 2 kT. In our discussion on diffusion, I will restrict attention to hard sphere molecules for gases. These are special molecules in the sense that the force between the molecules is infinite when they bounce off each other, but it is 0 otherwise. So, if the distance between molecules is larger than the molecular diameter, there is no interaction. This is an approximation for real molecular system. The actual molecular system shown on the right in blue, the force is attractive when the molecules come closer to each other, and then it becomes repulsive when they become very close. Okay. The hard sphere model that we will use is an approximation for the real molecular system. Okay. However, this enables us to make quick estimates which we cannot do using a real molecular system. Therefore, we will do the calculations for hard sphere molecular systems with the caveat that the scaling laws that you get, especially the temperature dependence of the diffusivities for real molecular systems could be slightly different from what we will calculate here. In particular, the calculation here for dilute gases of hard spheres, the diffusivity is proportional to square root of the absolute temperature. For real systems, it can have a different power, okay, but we will use the hard sphere system here so that we can make estimates. I had discussed the mechanism of diffusion. Okay. If you the molecular fluctuating velocities are what are called isotropic. The molecules fluctuate in all directions with equal probability. Okay. The distribution of velocities in all the directions is the same in all 3 directions. Okay. However, whenever there is a variation in the concentration, there will be a diffusive flux. The reason is that if across a surface, if there is a variation in the concentration, let us say the molecules of type A have a higher concentration above the surface and the molecules of type B have a lower type A have a lower concentration below the surface, the molecules that cross the surface cross from a distance approximately mean free path above the surface, right. Those that cross from above to below cross by a distance approximately 1 mean free path above the surface. Those molecules going from below to above cross the surface at a distance about 1 mean free path below the surface. There is a difference in concentration at these 2 locations. Therefore, you will have a greater number of molecules of type A coming downwards in comparison to the molecules of type A going upwards, and this results in a net flux of molecules, and this is the diffusive flux. I had done a simple calculation for you in order to estimate this diffusive flux. The molecules coming below the surface from above to below the surface come from a distance b lambda above the surface on average, where b is a constant factor and lambda is the mean free path the distance between intermolecular interactions. That is the microscopic scale in kinetic theory of gases. So, the molecules coming from above to below come from approximately a mean free path above the surface. At that location, the concentration is C A times Z at Z naught plus B lambda, if the surface is at Z naught. Okay. Okay. The flux of molecules is equal to the velocity perpendicular to the surface, the average velocity perpendicular to the surface times this concentration. And the average velocity we wrote as some factor times the root mean square velocity, where A is a factor, Aj is a factor which is smaller than 1, because the average velocity across the surface will be smaller than the mean free path, the isotropic mean free path of the molecules. Similarly, the molecules going upward come at a distance approximately 1 mean free path below the surface. Okay. And we had written down expansions for both of these, concentration above and below the surface, substituted that. Okay. And you can see that the value C naught cancels out in both cases, and you get a flux that depends only upon the variation dCA by dZ. It does not depend on the absolute value Ca itself, but only the variation of Ca with respect to distance. Okay. And this result has the same form as Fick's law, negative sign because there is a flux from higher concentration to lower concentration. In this case, higher concentration is above and lower concentration is below. Therefore, the gradient is positive, dCA by dZ is positive, the flux is downward. Okay. And we had got a value for the diffusion coefficient as some order 1 constants, some constants times the V root mean square times the mean free path. And we had estimated the means the root mean square velocity from equipartition, half m Vrms square is equal to 3 by 2 kT. Okay. And I had given estimates for the magnitudes of these as well for hydrogen, oxygen and nitrogen at room temperature and pressure. For hydrogen it is about close to 2000 meters per second, for oxygen and nitrogen approximately 500 meters per second. And both of these are comparable to the speed of sound. Okay. Both of these are comparable to the speed of sound in the material. Okay. Okay. So, the molecular fluctuating velocity is comparable to the speed of sound. The second parameter that we need to calculate here is the mean free path. Okay. So, how do we calculate the mean free path? So, if we take a gas, okay, and focus on one particular molecule, okay, it may undergo a collision, okay, with another molecule and change its velocity. Okay. And then it will travel some distance, okay, after which it will undergo another collision and once again change its velocity due to collision with another molecule, okay, in a gas which contains multiple molecules. Okay. What is the approximate distance between molecules? Okay. So, we can use the condition that two molecules will collide if the distance between their centers is equal to 1 molecular diameter dm. Okay. So, I will consider a gas of hard sphere molecules in which the molecular diameter is dm. Okay. Dm is the molecular diameter. As this molecule travels, okay, it traces out a cylinder. Okay. It traces out a cylinder, okay, of length L and radius equal to the molecular diameter. Okay. So, when the distance between two molecules is equal to the molecular diameter, that means two molecules have collided. Okay. So, it will trace out a cylinder in space as it is travelling of diameter of radius equal to the molecular diameter dm. Okay. such that if a center of a second molecule comes within the cylinder, that means that the two molecules have collided. Okay. And the number density of the molecules is n. Okay. 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 What is the number of second molecules in cylinder? Okay, the number of second molecules in the cylinder is going to be equal to the volume of the cylinder pi dm square. Okay. The cross sectional area is equal to pi dm square, because dm is the radius of the cylinder and pi dm square is the area, into L. That is the volume. The cross sectional area of the cylinder is pi dm square, pi r square, because r is equal to the diameter of the molecule, times L is the volume, times the number of molecules n. Okay. This is the number of second molecules that are within the cylinder, okay, as this molecule is going along. Of course, if it travels a small distance, this number of second molecules is small. That means that the probability of a collision is small. If you go over a very long distance, then the number of second molecules becomes large, which means that most likely this molecule would not have reached that distance, it would have collided before that. Okay. The approximate distance that it will travel before it collides is, okay, when pi dm square times L into n is approximately equal to 1, because that means that there is approximately a second molecule within that and the first molecule would have collided, okay, which means that lambda has to be proportional to 1 over pi dm square n. Okay. The mean free path, the distance between collisions, is when the number of second molecules in the cylinder traced out, this exclusion cylinder traced out by the first molecule, is approximately 1. That means that the lambda has got to be proportional to 1 over pi dm square times n. Okay. The actual formula for this mean free path is a little there is an additional factor here if you do a more exact calculation, and the mean free path turns out to be 1 over root 2 pi n dm square. Okay. So, that is the mean free path, or the distance between successive collisions of a molecule of diameter dm, number density n. You can easily verify that this has dimensions of length, because number n is number per unit volume, number per unit volume into diameter square, number per unit length in the denominator. So, effectively lambda has dimensions of length. Okay. So, this is the second factor in our expression for the diffusion coefficient. D is equal to 2 Aj V Vrms. Times lambda. Okay. So, this is the second factor. We can estimate this for gases. Okay. So, for example, let us estimate the mean free path for hydrogen in order to calculate the mean free path, you have to know the molecular diameter. Okay. So, I will give the molecular diameter dm is equal to 2.6 into 10 power minus 10. 2.6 angstroms is the molecular diameter, approximate molecular diameter of hydrogen. I told you that even though these molecules are actually diatomic molecules, we will approximate them as rigid spheres with one molecular diameter. This is the molecular diameter for hydrogen. Oxygen 3.7 and nitrogen at 300 Kelvin and atmospheric pressure. So, to estimate the mean free path, we need of course the diameter of the molecule. We also need to know what is the number density, number per unit volume, okay. And that number per unit volume is obtained from the ideal gas law, okay. The number per unit volume is equal to P by kBT. Okay. P by kBT is the number of molecules per unit volume. P by RT is the number of moles per unit volume. Okay. So, if I want to calculate actual number of molecules, which is what is required for the calculation of the mean free path, I actually require the number of molecules per unit volume. For that I have to use P by kT, okay, because Kb is the Boltzmann constant. Okay. Ideal gas constant will give you the number of moles, and then you have to multiply that by Avogadro number, okay, to get the number of molecules. Either calculation will give you the same result. Here I will just use kBT directly. Pressure 1.013 into 10 power 5 Pascal. Okay. Pascal is force per unit area. Okay. And Kb is 1.38 into 10 power minus 23 joules per Kelvin. It has dimensions of energy into 300 Kelvin. Okay. This will have dimensions of 1 over meter cube, because Pascal is force per unit area. Okay. And joules is energy, okay, and therefore, this the net result will be 2.45 to 10 power minus 5 meter per minus 3, okay, 10 power, I am sorry, not minus 5, 10 power 25. (2.45 into 10 power 25 per meter cube), that is 2.45 into 10 power 25 molecules per meter cubed of gas. Okay. So, that is the number of molecules per meter cubed of gas. Okay. This is the same whether it is hydrogen, nitrogen or oxygen. Okay. It does not matter. The number of molecules per unit volume is independent of the type of molecule in kinetic theory of gases. It depends only upon the pressure and temperature. Okay. So, this is the same. Okay. Using this we can calculate the mean free path. Okay. Lambda for H2, okay, is equal to 1 over root 2 pi, okay, into 2.45 to 10 power 25 meter per minus 3 into the molecular diameter, I said was 2.6 angstroms. Whole square. Okay. And if you calculate this, you will get this as 1.4 into 10 power minus 7 meters. Okay. Lambda of O2, n is the same, okay, root 2 pi. The number density is the same, 2.45 into 10 power 25 meter per minus 3 into the molecular diameter, which was 3.7 into 10 power minus 10 meters whole square. And this turns out to be 6.7 into 10 power minus 8 meters. Okay. Similarly, for the nitrogen. this turns out to be 6.4. Okay. So, to put this in perspective, 10 power minus 6 meters is a micron, okay. 10 power minus 3 meters is 1 millimeter, okay. 1 millimeter is equal to 10 power minus 3 meters, and 1 micrometer is equal to 10 power minus 6 meters. Okay. So, this is equal to 0.147 micrometers, okay, and this is equal to 0.067 micrometers. 10 power minus 9 is a nanometer. Okay. So, these are approximately 67 and 140 nanometers. Okay. So, the mean free path of a gas is approximately 0.1 micrometer. Okay. For hydrogen, a little larger mean free path because the diameter is less, and for oxygen and nitrogen the mean free path is lower because the diameter is larger. Okay. Now, you can calculate what is the ratio of the mean free path to the molecular diameter. Okay. So, you can calculate what is the ratio of the mean free path to the molecular diameter, okay. Lambda by dm, okay, of hydrogen, okay, is equal to 1.4 into 10 power 7 by 2.6 10 power minus 10 meters. Okay. This turns out to be equal to 5.2 into 10 power 2. Okay. Similarly, lambda of oxygen by the molecular diameter is equal to 0. Which is approximately 1.8 into 10 power 2. Okay. And similarly, lambda nitrogen by diameter, you can do the calculation, it turns out to be about 1.7 into 10 power 2. Okay. Lambda is the distance between successive collisions, dm is the molecular diameter. This implies that a hydrogen molecule travels more than 500 times its molecular diameter before it collides. An oxygen and nitrogen molecule close to 200 times its molecular diameter before it collides. So, the distance between collisions is actually much larger than the molecular diameter, as expected in kinetic theory of gases. Okay. In gases, the distance between molecules, the distance between molecular collisions is much larger than the molecular diameter. Okay. So, we can multiply this mean free path and the molecular velocity. Molecular velocity I told you is about 500 or so. Okay. Distance is about 6.7 into 10 power minus 8, and if you multiply these two, you will get about 10 power minus 5 as the diffusion coefficient in meter square per second. So, this is an approximate calculation of the diffusion coefficient. Okay. You can get a more exact formula, okay, DAB. Okay. The diffusion coefficient of A in B or vice versa, okay, is equal to 3 by 8 n DAB square into KB T MA plus MB by 2 by MA MB per half. Okay. Note that this term here has the same dimension as the RMS velocity, and this term here has the same dimension as the mean free path, and the factors that I have here, there is a 2 pi here and there is a 3 by 8 over here. Okay. So, this is an exact expression you can get from kinetic theory of gases, okay, for the molecular diffusion coefficients, okay, where DAB is the average diameter, dA plus dB by 2. Okay. And N is the number density, total number density. Okay. And for the self diffusion coefficient, that is molecules of A within A itself, okay, you just substitute MA is equal to MB and DAB is equal to DA, and you get this diffusion coefficient DAA is equal to 3 by 8 NA dA square, that is if you have only one component, okay, root of KB d by pi MA. Okay. So, these are more accurate estimates, okay, for the diffusion coefficient, which have explicit values for those parameters A, J and B that I had earlier. Okay. And we can use this also to calculate the diffusion coefficient in a gas of hard spheres. Okay. So, let us solve an example. Determine the diffusion coefficient of water vapor in air at atmospheric pressure and 300 K. Consider with So, in this case we are considering air has rather than oxygen and nitrogen, we just consider it as a single component with molecular weight 29 grams per mole, the average molecular weight, and molecular diameter 3.7 angstroms, because the diameter of oxygen and nitrogen are approximately the same. Okay. So, how do we get this? We have to use this expression. Okay. We have to use this expression here, where we calculate DAB and number density and the masses. Okay. So, the average diameter is equal to d air plus d water by 2, which is 3.15 angstroms. Okay. The molecular weight of air is equal to 0.018 kg, 18 grams, I am sorry, 29. By the Avogadro number in gram mole, which is 4.82 into 10 power minus 26 kg. The molecular weight of water is equal to 0.018, 18 grams. Okay. So, the diffusion coefficient 3 by 8. Okay. The number density was what we had earlier, okay, atmospheric pressure and 300 Kelvin. This is equal to 2.45 into 10 power 25 meter per minus 3. Okay. Okay. Into the diameter square 3.15 into 10 power minus 10 meters the whole square into square root of kBT. Kb is 1.38 into joules per Kelvin into 300 Kelvin into Ma plus Mb. Okay, so let me just write the expression here for DAB so that we. Okay. 8n DAB square root of kB d into Ma plus Mb by 2 pi Ma Mb. That was the expression we had on the previous screen. Okay. Ma plus Mb, the sum of the molecular masses, if you calculate it, will turn out to be equal to 7.81 into 10 power minus 26 kg by 2 into pi into Ma into Mb, that is 4.82 to 10 power minus 26 kg into 2.99 into 10 power minus 26 kg. So, this is the calculation you have to do, and ultimately you will get 2.9 into 10 power minus 5 meter square per second. Okay. 2.9 into 10 power minus 5 meter square per second is the diffusion coefficient of water in air. Okay. Reported diffusion coefficients in literature are 2.6 to 2.8 into 10 power minus 5 meter square per second. Okay. So, this prediction is remarkably close to what we get in actual experiments. Okay. So, this is just to demonstrate that what we have done here, the simple picture that we have, with this we are able to predict diffusion coefficients remarkably close to what we have from experiments. Okay. So, that is actually the power of this physical understanding. Okay. Just based upon a simple molecular picture and with expressions for the mean free path and so on, we were able to get a diffusion coefficient that was remarkably close to what we have in actual literature. In most gases, at room temperature and pressure, diffusion coefficients are of the order of 10 power minus 5 meter square per second. Okay. So, next class I will continue this. I will discuss mass diffusion in liquids, and then we will go on to thermal diffusion and momentum diffusion. In each of these cases I will motivate the form of the expression using kinetic theory of gases and a simple picture, and then I will discuss what the actual estimates are. I will continue this in the next lecture. I will see you then.